All right, let's get right into it. Today we're breaking down 1-bit Bonsai 8B. We're going to do a deep dive into the white paper and really unpack how they pulled off this end-to-end 1-bit language model.
So here's how we're going to tackle this. First, we'll talk about the big problem they're trying to solve, inference efficiency. Then we'll get into the nuts and bolts of Bonsai's 1-bit architecture. After that, we'll dig into the numbers, the actual performance evaluation. And to wrap it all up, we'll look at this really cool concept they introduced called intelligence density. It's a whole new way to think about how efficient these models are. Let's jump in.
Okay, so let's set the stage. For the longest time, the name of the game in AI was just train bigger models. But we've kind of hit an inflection point. Now the real frontier, the biggest headache, isn't training anymore. It's all about deployment.
And the researchers behind Bonsai put it perfectly with this quote. It really captures this shift in thinking. I mean, think about it. Every single time a user interacts with a model, every API call, that costs something. It costs latency, it costs energy, it costs real money for infrastructure. And this problem gets magnified like crazy when you start talking about running these things on the edge, on our phones, our laptops, you name it.
So, what's the real bottleneck here? You might think it's just raw compute, right? More GPUs, more power. But actually, especially for inference with small batch sizes, it's not. The real killer is memory bandwidth. It's like trying to drink a milkshake through a tiny coffee stir. It doesn't matter how powerful you are, you're limited by the straw. Your performance is literally capped by how fast you can shovel the model's weights out of memory. This means the model's physical size, its footprint, suddenly becomes the most important thing to solve for.
Now look, the idea of a 1-bit model isn't some brand new concept. People have been trying this for a while. But making them actually work in the real world has been a massive challenge. See, when these things fail, they don't just get a little worse. It's not a gentle slide in accuracy. No, it's more like falling off a cliff. The model just completely breaks down, losing its ability to do complex things like multi-step reasoning. On top of that, a lot of the older approaches needed all this custom, specialized code, custom kernels, weird runtimes, which just makes them a nightmare to actually deploy.
So that brings us to the solution. Let's talk about Bonsai's 1-bit architecture and how it's designed to smash through that memory bandwidth bottleneck we were just talking about.
Okay, the secret sauce here is their quantization format. It's called Q1_0_G128. And it's actually pretty clever. Here's the deal. Each individual weight is stored as just one single bit. Yep, basically representing positive or negative. But then, for every group of 128 of these tiny weights, they have one shared, high-precision FP16 scale factor. So when you do the math, right, you've got 1 bit for the weight plus a little piece of a 16-bit number for the scale factor. That comes out to an effective 1.125 bits per weight. It is just incredibly efficient.
And the result of this? I mean, just look at these numbers from the paper. It's kind of insane. The original full-fat FP16 model is a chunky 16+ gigabytes, but the Bonsai version? It comes in at just 1.15 gigs. That's not a typo. That's a 93% reduction. It's more than 14 times smaller. For anything running on device, this isn't just an improvement. It's a total game changer.
Okay, so it's tiny. That's awesome. But the big question, the one we all have, is, does it still work? I mean, if you shrink something that much, does it just fall apart? Let's look at the actual data on speed, efficiency, and of course, whether it's still smart.
First things first, let's talk about speed. How many tokens per second can this thing actually crank out? And what's cool is they tested it across a bunch of different hardware, which is exactly what you want to see for a model like this.
And yeah, the results are, well, they're pretty wild. On a beastly RTX 4090, you're looking at a 6.2x speedup over the baseline. On Apple's M4 Pro chip, it gets even crazier, an 8.4 times speedup. And check this out, on an iPhone, the full model is so big it won't even run, so they had to compare it to a 4-bit model, and Bonsai is still more than 3 times faster. This isn't just a small win, it's a huge throughput boost everywhere.
All right, speed is one thing, but what about power? Especially for mobile and edge devices, energy efficiency is everything. We're talking about battery life, but also the long-term cost of running these models in the cloud.
Now, this is a really interesting and kind of counterintuitive point. The paper points out that at any given instant, the 1-bit model might actually be drawing more power. It's like a sprinter using a huge burst of energy. But because it finishes the race, generates the token, so much faster, the total energy it uses for that one token is way, way lower. On the M4 Pro, it's a 5.6x advantage. On the 4090, a 4.1x advantage. It works harder for a shorter time and ends up saving a ton of energy overall. Okay, so let's recap. It's tiny, it's fast, it's energy efficient, but this is the moment of truth. Is it still any good? Did all that compression just lobotomize the model?
Well, this table pretty much answers that question. Take a look. At just over 1 gigabyte, 1-bit Bonsai scores a 70.5 average on the benchmarks. That's really, really good. It's right there in the same league as full-sized, full-precision models like Almo 3 and Llama 3.1, which, remember, are more than 14 times bigger. Sure, it's a little behind its original base model, Qwen 3, but the fact that it's this close is just incredible. The intelligence is absolutely still there.
And this is where things get really interesting. Because the model is so small, yet so capable, the researchers realized we might need a new way to even talk about this. And that's what led them to coin this term, intelligence density.
So they ask a really fundamental question. How should we actually measure how good a model is? Is it just the raw benchmark score? Is it just the file size? Or is there a better way to capture the bang for your buck? How much smarts are you getting for every single byte you have to store? This is their answer. Intelligence density. The formula is rooted in information theory, but the core idea is simple. It looks at a model's intelligence, specifically how unlikely it is to make an error, and then divides that by its size. And the really clever part is how it measures intelligence. It knows that getting better gets harder the better you are. Climbing from a 90 to a 99% score is way harder than going from 50 to 60. This formula accounts for that, giving us a much more honest measure of intelligence per gigabyte.
And when you actually apply this metric, the results are just shocking. The Bonsai models are complete outliers. The 8B version clocks in with an intelligence density of 1.06. Now compare that to its parent model, the big Qwen 3 8B. It's at 0.096. That's not even close. We're talking about a completely different league of efficiency here.
Yeah, this chart says it all, doesn't it? The difference isn't small, it's a chasm. Using this smarter metric, the 1-bit Bonsai model gives you more than 10 times the intelligence for its size compared to the original. Just wow!
So what does this all mean? The big takeaway here is that Bonsai isn't just a slightly better point on the old trade-off curve between size and smarts. It's like they drew a whole new curve. They've fundamentally shifted what we thought was possible, creating a new standard for what efficient AI deployment looks like.
So let's just recap the highlights. We're looking at a model that's over 14 times smaller. It's up to 8 times faster at generating tokens. It uses up to 6 times less energy to do it. And somehow, it does all this while staying competitive with giant, full-precision models and delivering over 10 times the intelligence density. The numbers are just staggering.
And that brings us to the final, and maybe most exciting question. Everything we've seen today, all these incredible gains, this was all done in software, on the general-purpose hardware we already have. So it just makes you wonder, right? What happens next? What happens when we start building chips, designing silicon from the ground up, specifically optimized for this kind of 1-bit math? What kind of future does that unlock for powerful AI that can run on literally everything?